Alright guys, here's the last video of this review session thing, or this might be two videos, but here's the last problem. So estimate the time required for the water depth of the reservoir shown in the figure to below to drop from a height of 25 meters to 5 meters, and the connections are threaded. So this is a Bernoulli equation problem. So we're going to pick one point up here and then one point down here, right? Because this is a free jet and this is a large tank. So that'll make our lives pretty easy. So, right, with Bernoulli, I'm going to use this this version of it just because I'm almost sneezing like 5 times. Wait. There it is. Okay. It's allergy season. Anyway. Just so we see this at least once. Alright. So I ran out of room up here. That's what I wrote down. And we know that P1 equals P2 open the atmosphere, so we're just going to say that's 0. And there's no pumps or anything like that, so we are at the work shaft head is, or the work shaft is 0. And then the velocity at point 1 is 0. So what you might be tempted to do is say, hey, how about I just call this elevation here 55 meters and this elevation here 0 meters? Well, the issue with that is that what's happening here is, right, this is decreasing, right? So this elevation here for point 1 is going to be changing. So why can we say V1 is still 0? Well, we can still say that this is a relatively large enough tank and that the velocity is going to be close enough to 0 that we can consider it to be that anyway. And you'll see from the time that we get that that's a pretty fair estimate, honestly. So you'll see that as we finish this problem. So plugging in these values and then shuffling some stuff around, we get G times Z1 minus Z2 is equal to V2 squared over 2 plus G times HL. And we're going to denote Z1 minus Z2 as H plus 30, right? So we're going to call the distance from here to the surface of the water, or point 1, H. So our Z1 we can call H plus 30, and our Z2 we can call 0. So we can just call the difference H plus 30. All right. And then we'll solve for a velocity, and then we'll figure out what our HL is. So rewriting this a little bit, we have G times H plus 30 is equal to V squared over 2. I'm calling this just V because whatever V is happening here is going to be the same V that's inside the pipe. So we're not going to have a problem there. And then G times HL, so that's friction times the length of the pipe over the diameter of the pipe, plus R sigma KL. And what we have is we have a reentrant, elbow 1, 2, and 3. So 3 elbows, right? Let me double check this real quick. And then a globe valve and our, let's see. Yeah, that's it. All right, because this exit's not going to be doing anything. So let's see. Oh, nope, just kidding. There's 5 elbows. That's why. 5 regular 90-degree elbows. Okay. Oh, because it's going to do a 1, 2, 3, 4, 5 thing? I don't know. 1, 2, 3, 4, 5. That's what it's doing. There's like a little 3D thing going on with it. But anyway, it tells us there's 5 elbows, so it's not just the 1, 2, 3. Anyway, so we have then plus 5 times KL elbow plus KL of the globe plus KL of the reentrant multiplied by v squared over 2. Do G? No, that's right. Okay, never mind. All right. Anyway, so what we'll get, v squared over 2. If we want to, we're rewriting v squared over 2 in terms of our flow rate, which is 8 q squared over pi squared d to the 4th. And then putting this back up into here, and then solving this whole thing for q, we get q is equal to pi times d squared multiplied by, let me write it out before I say it, 8 plus times over d plus 5 KL elbow plus KL globe plus KL reentrant multiplied by g times h plus 30. And this is the square root. Alrighty. So next thing we're going to do is plug all of the numbers that we know in. So pi times our diameter is 0.07 squared. 8 stays the same. 1 plus, we don't know our friction factor yet. We know our length is 1,000 meters. We know the diameter. KL of an elbow is 1.5. KL of a globe valve is 10. And our reentrant 0.8. Those aren't numbers you're going to have to memorize, but they'll be somewhere on the exam. You just have to find them. But if you know them off the top of your head, that works too. Oh, hello. My bad, I wasn't even paying attention. Sorry, that was off the dot cam. I'll just leave this here real quick if you want to pause the video and write it out. Alrighty. So hopefully you got the chance to write it all out so far. If you haven't, I'll do that real quick. Alrighty. So, we're just going to go ahead and put all these numbers together. Make this look a little bit less like such a mess. There we go. So now we have a function for our Q, but we don't know what our friction factor is. So to get a friction factor, we need a Reynolds number. That's the old problem. So I'm going to flip this over. If you want to write all the work down, there's that. All right. So, there are my notes. So Reynolds number, so we can get our value for our friction factor, right? VD over nu, which is the same as 4 times Q, pi times diameter nu, right? Because that's the value we got for our velocity. And then this is 4 times Q, or pi times 0.07 times 1.31 times 10 to the negative 6th equal to 1.39 times 10 to the 7th multiplied by Q. And we know epsilon over D. Ooh, let me make sure this focuses real quick. All right, epsilon over D, 0.15. Convert that real quick into, I believe, it's centimeters, or is that meters? yeah, 7 centimeters, so we're converting this to centimeters as well. We get, what do we get? One sec. 0.00214. So we have a Reynolds number, we have epsilon over d, and we have our Q in terms of a friction factor. So we can assume wholly turbulent flow or use our iteration process or the Colebrook equation or the Holland equation. Whatever you do, you should get F is 0.0258. And then we get our flow rate is 0.017 times the square root. We'll write this at 193 plus 14300 multiplied by that friction factor that we just found, H plus 30. All right. Writing that out, or multiplying all the numbers together, 0.000863 times the square root of H plus 30. Wow. So the problem is we've run out of equations that we know, and we are still left with 2 unknowns. So I'm going to go ahead and stop this video here. So we know that, let me just say this. So the flow rate is a function of, it decreases, so it's the area, and it decreases with time with respect to h. So, and the square area we're given is 500 dH dt. Right, because our flow rate is the volume that we're given, so that would be a square area times the height, and then per time. But we don't know the height because that's changing, and so that should be dt, not ht. Anyway, so this is the function that we have. We have this one and this one. And I'll go ahead and stop the video here. If you guys want to try working the solution from here and then checking the second video, I would suggest doing that. But if not, you can just move on to the next video.